All right, folks, welcome back. This is the one of the last things we're going to do in this chapter. It's called Differential Equation Summary, and this really is what I have called in other chapters like big ideas. So this really incorporates everything that we've talked about in this chapter. I'm not going to read everything to you because I'm pretty sure you know how to read. I believe that skill was taught to you in prior grades. So what I'm going to do is just highlight some of the big ideas. First of all, it says a differential equation is a mathematical equation that relates some function with its derivatives. In applications, the functions usually represent physical quantities and the derivatives represent their rates of change. So anytime we have a differential equation, the function is a quantity, the derivative is a rate of change. All right, folks, so that's the basics here, and then separable differential equations. The only type you'll be asked to solve in AP Calculus AB is a differential equation that is separable. What I'd like to do quickly is show you an example of one that is not separable, just so you have kind of an example of that. Let's say dy dx equals x plus y. If you were to try to separate that, you would get dy equals the quantity x plus y dx, and here's why you can't separate that, because this quantity is added together multiplied by dx. You can't separate out the x plus y. If you tried to distribute the dx, then you would end up having a bigger mess. So that is an example of what I mean by not separable. You can't separate that x plus y from the other components in the differential equation. Okay, general solution. After separating variables and we find a general solution, it's going to have a plus c in it. Don't forget about that plus c, please. Sketching particular solutions, we do that on a slope field. Identify the initial condition, then sketch a curve in both directions following the lines of the slope field as a guide. Big idea here, do not cross any asymptotes of the differential equation. I'm going to tell you why that's important. I've said it in previous lessons, but it's worth repeating again, so bear with me here. If we have a differential equation, that implies differentiable, which in turn implies continuous. When finding particular solutions, make sure you solve for that constant of integration by substituting in some initial condition. I call it initial condition here. That does not mean that the input x or t has to be equal to 0. It can be any point on the graph. Last but not least, don't forget to specify the domain of your solution. To do that, you identify the single open interval that contains the initial condition, while making sure the differential equation is defined and true for all values on the interval. Okay, so let's go ahead, and the rest of this is just two examples. There's one differential equation we'll solve on the front here, and then one on the back, and then I asked you to find some particular solutions and sketch their graphs on a slope field. So let's go ahead and jump at this first one. We're going to go through the four-step process here. We're going to write the differential equation first. We have dy dx equals x over y for y not equal to 0. That's important to note there because we have a y in the denominator. So let's rip through the procedure. When we anti-differentiate this bad boy, we get y squared over 2 equals x squared over 2 plus some constant. So let's now go through our rewrite step. I'm going to start by multiplying out everything by 2. It's a different constant than it was before, so I'm going to go ahead and tag it with a different subscript. We want to solve for y here, so we're going to go ahead and say we're going to extract a square root from both sides. So we have y equals either the positive or the negative square root of x squared plus c. So this is our general solution. And there's a couple things I'd like to mention here. So we have to select a positive or negative value. We can't leave it like this because that's not a function. We have to select either the positive or negative square root based on the initial condition. We also have to remember y cannot equal 0. And in case you forgot, y equals 0 is the x-axis. So we cannot cross the x-axis with whatever solution we come up with. Okay, now let's go ahead. We're done with the general solution. Let's jump down here and find particular solutions through a couple points. First initial condition here we have is -2, 1. So we're going to substitute in the x value of -2, y value of +1. Just note here, if y equals 1, that means y is greater than 0. So we're going to need to keep that in mind when we select the sign of our particular solution. So again, we had y equals either the positive or negative square root of x squared plus c. Well, since y is greater than 0, we are going to select the positive square root. And now let's substitute in y equals 1, x equals -2. And we're left with 1 equals the square root of 4 plus c. That means 4 plus c has to equal 1, which gives us a value of c equals -3. So that's our constant of integration. Let's go ahead and write out our particular solution. There's our particular solution, y equals x squared minus 3, but we're not done just yet, and I want to go back up here and highlight one thing. Domain. Identify the single open interval that contains the initial condition while making sure the differential equation is defined and true for all values on the interval. So we have to make sure that whatever domain we specify includes this, x equals -2 and y equals -1. We have a y value that has to be greater than 0. We took care of that by including the positive sign there. And then we have to make sure y does not equal 0. So that means we have to analyze what's under the square root symbol. So let's take a quick look at that. What happens if we try to solve this equation, x squared minus 3 equals 0? Well, we know that x can equal positive or negative square root of 3. Let's just take a quick look at a sign chart to kind of talk about this expression, x squared minus 3. So we know that expression equals 0 at -√3 and +√3. So I'll mark my sign chart accordingly. Now if I pick a value over to the right of the square root of 3, something like, let's just say 10 squared minus 3, it's positive, so we're good to go there. We don't have a negative sign under the square root. Let's do the same thing to the left of -3. -√3, let's pick something like -10. You square that, you get a positive 100. You subtract 3, we're still good under the square root symbol. The problem though happens in between these 2 points. If we plug in something like 0, we have the square root of -3, and that's undefined. So we now need to pick a single open interval which contains the initial condition and doesn't violate any rules of the function. So we have x equals -2. That's going to be on this interval over here. So we are going to say for x less than -√3. That is our final answer for this particular solution. Let's go ahead and look at it and graph it real quick. We've got the initial condition of -2, 1 right there. We're going to sketch through that point, not crossing the x-axis, and following the path of the slope field. There you have it. Notice I put an open circle there. That happens to be at -√3, which is about -1.7. Okay, let's jump down to the next particular solution we need to find. That's for the initial condition -1, -3. Same strategy here. In this case, we have y less than 0, so that's going to determine what sign we select on our particular solution. So let's go ahead and sub that value in. We have y equals, we're going to select the negative square root of the quantity x squared plus c because y is less than 0. So to solve this, we need this quantity under the square root symbol to equal 9. 1 plus c has to equal 9. That means c equals 8. Let's go ahead and see what that looks like in a particular solution. Y equals the opposite of the square root of x squared plus 8. If you're wondering why, folks, I did jump through this real quick. Why does this quantity have to equal 9? Well, because I need the square root of that number to be 3. Okay, let's continue on and think about now, how do we make sure y doesn't equal 0 here? Well, x squared plus 8, y would only equal 0 if x squared plus 8 was equal to 0. But x squared plus 8 is greater than 0 for all x. And that's exciting because that's now our domain for all real x. Sometimes I don't specify that it's real, but that's kind of implied in the course we're working in, but there I'll be specific. Let's go ahead and graph it on the slope field. I have a point at -1 comma -3. And I'm going to follow the slope field through there. And there you have it. There's our particular solution. All right, folks, let's go ahead and shut this one down and do page 2 in another video.